All right, I'm going to give a few minutes for folks to be filtering in here. Like the rest of you, I am patiently and impatiently watching the Electoral College votes tick up for both candidates and anxiously waiting to see if we get a little tip back in the direction of sanity for this country in the next 4 years. But we'll have to see. In the meantime, there is stuff for us to talk about, namely power series. So I'm going to shift over here. Looks like most folks are arriving. So let's go ahead and do the thing. Some fresh pens today. It's nice. Today, we're talking about power series, which is, I'm going to cover a few sections, but we're going to focus on section 11.8 today. In the next few weeks, we are going to continue working with series a little bit. Although the question is going to shift from like, does this series converge or diverge? There will still be that, but it will shift from that being the main question towards something else being the main question. In particular, the power series representations of functions. The main kind of techniques and stuff that you're going to need to remember moving from the earlier bits of chapter 11 to where we are now are the ratio test, the results on geometric series, and the estimation theorem for alternating series. Those are the three things that we're going to be using more than anything else. And that was the ratio test, the resultant theorem on geometric series, and the estimation theorem for alternating series. But getting into the actual material, what is a power series? Well, a power series is an expression of the form f of x equals sigma n from 0 to infinity Cn times x minus a to the n. Right, so it's a series. You got your capital sigma here, it's a series. And you've got some numbers, Cn, which are multiplying x minus a to the n. So the number a here is called the center. And the numbers Cn here are called the coefficients. And if you want to write that out in long form without the capital sigma, it looks like C0 plus C1 times x minus a plus C2 times x minus a squared plus C3 times x minus a cubed, and so on. Got two more little definitions for you. Associated with every power series is a number, capital R, which is greater than or equal to 0, called the radius of convergence. And the idea here is that such that if x is within r units of the center, then the power series converges absolutely. All right. I've got an alarm going off in the other room. I'm going to turn that off while you write this. All right. So here's the idea. Here's an interval of x values. Here's the center, A. That's the number A here, right, in this expansion. If you go left and right by r units, so starting at A and going to the right r units, I'll go to A plus r. Starting at A and going to the left r units, I would land over here at A minus r. If you take an x value from anywhere in here, the series is guaranteed to converge. All right. So these series, they have x's in them, right? X minus a to the n. So some x's you could plug in and get a convergent series. And maybe if you plug in x equals 0, you get a convergent series. But if you plug in x equals 10, you get a divergent series. Our goal is to kind of find the set of all x's you can plug in so that the series converges. One of the neat tricks for doing that is to find this number r, called the radius of convergence. Once you find that number r, you know that as long as you stay within r units of the center, as long as you don't wander further than r away from the center, the series will converge. The other kind of preliminary definition here is the interval of convergence. So associated with every power series, sigma cn x minus a to the n, again, summed from wherever to infinity, I'll say 0, is an interval of the form. It's either going to be the open interval a minus r to a plus r, the left closed and right open interval, the left open and right closed interval, or the closed on both sides interval, such that the series converges for all x values coming from that interval. This is called the interval of convergence. All right, so the radius of convergence is how far you can walk from the center and still be guaranteed inside the interval of convergence. The interval of convergence is the interval a minus r to a plus r but you don't know whether it's open, left closed, right open, left open, right closed, or closed on both sides. The interval of convergence is the interval of all the x values that you can plug into your series so that the series converges. These things turn out to be connected. The interval of convergence is always symmetric about A. And the radius of that interval, if you think of it as like a one-dimensional circle, the distance from the center to the boundary is called the radius of convergence. Okay. So let's look at some examples.
Can I write that last bit down still?
Oh, that's close.
Okay, I'm good.
Okay, so let's look at some examples. Let's take some series and find their interval, radius and interval of convergence. Let's see what we can learn about some power series. This thing you've seen before. This is actually a power series. This is a power series. The center, A, is 0. Coefficients, Cn are equal to 1 for all n. What's more, this power series happens to be a geometric series. The common ratio here is x. So the series will converge if and only if the absolute value of x is less than 1, which is the same as saying -1 is less than x is less than 1, i.e., the interval of convergence is the open interval from -1 to 1, which we can draw. I'll put my center here. -1 is here, 1 is here. So my radius of convergence is r equals 1. So here, in other words, we get lucky. The power series we're messing with turns out to be a geometric series. All right, the series sigma x to the n, that's definitely geometric. The common ratio is x. So without any sort of fancy tricks, without having to use the ratio test or anything like that, I'm able to find exactly what x values give me a convergent series. Since it's a geometric series with common ratio x, the series will converge if and only if the absolute value of x is less than 1. That means x comes from the open interval -1 to 1. Another example of a power series let's say 1 over 2 to the n times x minus 1 to the n. This is also a power series. A, the center here, is equal to 1, and Cn, the coefficients here, are 1 over 2 to the n. Okay. So I know where my series is centered. I could start trying to draw the IOC here. I know it's going to be centered at 1, my interval of convergence, but I don't know what my radius of convergence is yet. I don't know how far I can reach in either direction there. But if you pay attention, this is also geometric. I can treat this as sigma n from 0 to infinity 1/2 1 over 2 to the n times x minus 1 to the n. But just doing some algebra, that's the same as sigma n from 0 to infinity x minus 1 over 2 all to the n. So here the common ratio is x minus 1 over 2. So this series will converge provided absolute value of r is less than 1. That's always true for geometric series. And here, that's the same as saying the absolute value of x minus 1 over 2 is less than 1. Absolute value of x minus 1 over 2 is the same as absolute x minus 1 over 2, like this, because the absolute value of 2 is 2. And then I can multiply both sides by 2 to get absolute x minus 1 is less than 2. I'm going to continue working with this inequality. Now I can unpack the absolute value statement as negative 2 is less than x minus 1 is less than positive 2. And then finally, I can add 1 everywhere. Negative 2 plus 1 is negative 1. So negative 1 is less than x is less than 3. So in other words, I know now the left endpoint is negative 1, and I know that the right endpoint is 3. So this distance is 2. And you notice it's symmetric on both sides, right? So my radius of convergence which you'll see me abbreviate as ROC, radius of convergence, is 2. And the IOC, interval of convergence, is the open interval from negative 1 to 3. Questions on these two examples here?
When would you use brackets?
So because both of the examples we've looked at are geometric series, we know that they'll only converge when the common ratio is strictly less than 1. So when you're dealing with a geometric series, the interval of convergence will always be open because you always need your common ratio to be strictly less than 1. And that's always going to correspond to a strict inequality for x. But if I give you some power series that are not geometric, then you'll start seeing some different looking intervals of convergence. So that's a good question. I will show you some examples like that in just a second. But for now, I wanted to make sure that we're comfortable with the basic idea that the center is always like the center of the interval of convergence, that the radius of convergence is the distance from the center to the edge of the IOC, and then just sort of the basics of this inequality work here. So are we all comfortable with like this step? This is an important step. Unpacking that absolute value. Does everybody see what we did here? Are there any questions about this? The more general rule is this. If you've got the absolute value of some shit is less than a constant, that's the same as saying that that shit is bigger than the negative version of that constant and smaller than the positive version of that constant, no matter what the shit is. So here the shit was x minus 1 and the constant was 2. So x minus 1 is bigger than negative 2 and smaller than positive 2. These are equivalent. And this sort of unpacking process is always necessary at some point in these problems. All right, let's look at a more complicated example. So let's find the ROC and the IOC of the power series. Call it capital F of x equals sigma n from 0 to infinity, negative 1 to the n over n plus 1 times x to the n plus 1. This is not a geometric series because it's not just a bunch of stuff raised to the nth power. This n plus 1 down here messes up the geometricness. So instead of using what we know about geometric series, we have to use something else. And the something else is the ratio test. Pretty much always when working with power series, if the thing ain't geometric, you're going to use the ratio test. So it says L is the limit as n goes to infinity, absolute value of an plus 1 over an, which in this case is the limit as n goes to infinity of the absolute value of, let's see, that's negative 1 to the n plus 1 over n plus 1 plus 1, that's n plus 2, and then x to the n plus 2. So there's an plus 1. And now I'm going to multiply by the reciprocal of an, which is n plus 1 over negative 1 to the n times x to the n plus 1. Does everybody see why this is the ratio test limit for this series? This stuff right here is an, the whole thing. So an plus 1, I just swap all the n's for n plus 1s. That gives me negative 1 to the n plus 1, x to the n plus 2 over n plus 2. That's this piece. And then I'm dividing by an. So I'm going to multiply by the reciprocal of an. So I just take an and I flip it over, I get this. Now, just like I would do in any of these other problems, I want to kind of put these pieces together. So I have x to the n plus 2 over x to the n plus 1. Let me put those together. I have negative 1 to the n plus 1 over negative 1 to the n. And I have n plus 1 over n plus 2. So these are all my pieces. I can give each one their own absolute value because absolute values are multiplicative. And some of this shit is easy to work out, some of it's hard. Well, none of it's really hard, but x to the n plus 2 divided by x to the n plus 1, just subtract the powers. N plus 2 minus n plus 1, that's 1. So this is just x to the 1. So here I have lim n to infinity, absolute value of x times negative 1 to the n plus 1 minus negative 1 to the n. That's the absolute value of negative 1 times absolute n plus 1 over n plus 2. Well, n plus 1 and n plus 2 are both positive, so this is just n plus 1 over n plus 2. The absolute value of negative 1 is 1. So this piece can fuck off. It's just multiplying by 1. It's not doing anything. This piece doesn't have any n's in it, so we can come outside the limit. And I get absolute value of x times lim n to infinity n plus 1 over n plus 2. What is this limit?
One half.
If n was going to 0, that would be 1/2.
Would it just be 1?
Yeah, this is 1. Yeah, this piece is 1. So this is absolute value of x times 1, or just the absolute value of x. All right. So L is equal to the absolute value of x for this series, which means L is less than 1 if and only if the absolute value of x is less than 1. See what I mean about these absolute value inequalities coming back? Even when we're not looking at a geometric series. This is equivalent to saying negative 1 is less than x is less than 1. So if I go drawing my IOC, this series was centered at 0. Right, the center here is 0. Because x to the n plus 1 is the same as x minus 0 to the n plus 1. So now I have an idea of what my IOC looks like. But you need to think very carefully. If L is equal to the absolute value of x, then it's true that L will be strictly less than 1 only when x comes from this open interval. But remember, with the ratio test, L equals 1 is inconclusive. If L is strictly less than 1, the series converges. If L is bigger than 1, the series diverges. But we don't know what happens when L is equal to 1. That can go both ways. In other words, these endpoints, -1 and 1, we don't yet know whether the series converges at those endpoints or not. And this is the way most of these problems go. After you get this, now you need to check the endpoints. So we need to go back and individually check those two endpoints. When x is equal to 1, my series is sigma n from 0 to infinity, negative 1 to the n over n plus 1 times 1 to the n plus 1, which is sigma n from 0 to infinity, negative 1 to the n over n plus 1. Does this series converge or diverge? Taking all bets. What do we think? You can guess. There's no harm in guessing. I'm curious what you guys think.
Diverge.
Okay. Why do we think this series diverges? If it's just a guess, that's okay too. Nathaniel, why do you think this series converges?
I'd say it converges too.
Okay, I'd be curious to hear why. Sergio, Nathaniel?
I'd say why, because like if you plug in 0 as n equals 0, the top would be 1 and the bottom would be 1. So 1 over 1 is 1, or negative 1 at least.
Right, but that doesn't tell us whether the series converges or diverges.
Correct.
Just a sec.
Sorry for
Would
that,
it be
but yeah, no.
convergent because when you take the absolute value of the top, you're always going to have 1, and then you would have 1 over n plus 1, and as n approaches infinity, you'd be getting 1 over infinity, basically?
Well, that would prove that it gets past the test for divergence. That would prove that the ANs here do go to 0, but that's not enough to say the series converges either. Nathaniel has it in the chat. AST. This is a conditionally convergent series, but it is a convergent series, and it converges by the alternating series test. Here the BNs are 1 over n plus 1. These are decreasing. And the limit as n goes to infinity of the BNs is 0. So here, as an alternating series, we're able to say that this is a convergent series. If you take absolute values inside, you get 1 over n plus 1. That's a divergent series. All right, sigma 1 over n plus 1 without the negative 1 to the n diverges. You can do a limit comparison to the harmonic series. In fact, it is the harmonic series. It's just a shifted version of the harmonic series. So at the end of these problems, after you get the endpoints here, you need to test the endpoints one at a time. Each one of those is going to be like a problem from 11.6 or 11.5, where you need to go back and use one of the other convergence tests. What about at x equals negative 1? If I plug negative 1 into my function here, into my series, I have sigma n from 0 to infinity, negative 1 to the n over n plus 1 times negative 1 to the n plus 1. Negative 1 to the n times negative 1 to the n plus 1 is negative 1 to the 2n plus 1. So this is what I get. And since 2n plus 1 is always odd, -1 to the 2n plus 1 is always -1. So this is just negative sigma n from 0 to infinity 1 over n plus 1. This diverges by a limit comparison with sigma 1 over n. So we really got to get to a place where you have some intuition, a good feeling for what's going on with these series. The standards to which I am going to hold you in your homework, your study guides, your exam 3, you got to do all the normal ratio test stuff to get to here. But then when you start checking your endpoints, if you tell me correctly whether the series converges or diverges, and you're able to cite the test that would do the job, then I will trust that you actually know whether the series converge or diverge. You weren't just guessing. In practice, you may want to, when you get to this step, run the alternating series test. Or when you get to this step, you might want to actually run the limit comparison test and make sure you know what's going on. But once you get a little bit more proficient, a little bit more comfy, this won't be hard. And this is why I was saying if you're really comfy with the material from 11.1 through 11.6 or 11.1 through 11.7, then 11.8 won't be hard. But if you're not comfy with that material, then 11.8 will be hard. You need to know your convergence tests. We'll be using primarily the ratio test, right? When it comes to actual raw calculation here, we're using the ratio test. But then when it gets to the endpoints, you do need to be ready to use all the other tests as well. Or at least ready to refer to them. So what can we say here? My series is centered at 0, has radius of convergence 1, converges when x is equal to +1, diverges when x is equal to -1. So which of the following is my interval of convergence? Is it the open interval from -1 to 1? The left closed right open interval from -1 to 1? The left open right closed interval from -1 to 1? Or the closed interval from -1 to 1? Well, my series converges when x is equal to 1, which means 1 has to be in my IOC. So it's either this guy or this guy. These are the only two that contain 1.
Would it be the third one?
Yeah, good. And the series diverges when x is equal to -1. So it can't be this guy. It's got to be this fellow. X equals 1 is in my series. X equals -1 is not in my series. In my interval, sorry, series. My series converges when I plug in x equals 1, which means 1 is in my interval of convergence. My series diverges when I plug in x equals -1, which means -1 is not in my interval of convergence. So it had to be one of these. And the only one whose endpoints match are this guy. Had to be one of these, a -1 to 1, because my center was 0, and this inequality told me that the values of x which I'm guaranteed convergence are those strictly between -1 and 1. All right, and my radius of convergence, we could have said this all the way back here, the radius of convergence is 1. Okay, how are we feeling? We feeling comfy about this example? Feel like we get it?
Yeah, a quick question. How was the limit as n approaches infinity of n plus 1 over n plus 2? How is that equal to 1?
L'Hopital's rule or renormalization or the limit tricks we learned. And the way I've been teaching it in this class is you should renormalize, but there's a lot of ways to this. The horizontal asymptote for this is 1. If you divide top and bottom by n,
Okay, gotcha. Never mind.
that's 1 plus 0 over 1 plus 0. It's a fair question. Other questions on this?
Yeah, another question. So how come with the geometric series we used parentheses instead of the brackets?
Well, because the geometric series, we didn't need the ratio test for. Geometric series converge only when the common ratio is strictly less than 1 in size. So we were able to just solve an inequality like this and know for sure that those were all the x values for which the series converged. But here, because this was not a geometric series, I had to use the ratio test. And with the ratio test, when L is less than 1, you're guaranteed that your series converges. But when L is equal to 1, you don't know what happens. So here, when x is equal to -1, or when x is equal to +1, that's when L is 1, and those are inconclusive. So we had to look at those separately. We found that when x is equal to +1, we did get a convergent series. So we included +1 in my IOC. But when x is equal to -1, we got a divergent series. So I don't include -1 in my IOC. So if the series you're working with is geometric, then there's no need to test endpoints because geometric series always converge just when the common ratio is strictly less than 1. Like you can get it just from solving this inequality. If you're using the ratio test, then after you solve this inequality, you need to separately consider the cases where L is equal to 1. Here, L is equal to 1 when x is 1 and when x is -1. So we had to consider those cases separate from the rest. So the kind of upshot here is if your power series is geometric, you don't need to test endpoints. But IOC will always be open. If your power series is not geometric, then you do need to test the endpoints. The IOC could be open, closed, or half open. All right, open on the left, closed on the right, whatever, like it is above. So if you're lucky, if the power series you're messing with is a geometric series, then we know everything there is to know about geometric series. There's no mystery, there's no need for a ratio test, there's no need for any special testing. Most power series are not geometric though. Most of the time, you're going to need to run the ratio test. Then after running the ratio test, you're going to need to check the endpoints. Just like the example we did a second ago. But I'll take a second and look at an example or two with you here in the book. In section 11.8. Those are 11, 7. So they start with the example we started with there, talking about geometric series. But come on, motherfucker. All right, let's classify these according to whether or not they are or are not geometric. This is not geometric because of the n here. This is not geometric. This is not geometric. This is not geometric. If it didn't have the n to the 4 downstairs, it would be geometric. X to the n over 4 to the n, that would be geometric. But as it is, it's not. This is not geometric because of the square root n. This is not geometric because of the n over n squared plus 1. In fact, very few of these are geometric. This is not geometric because the n to the n downstairs, that base n, is not constant. In fact, I don't see any of these which are geometric. So very, very rarely are your power series geometric series. The first two examples we looked at were, because those are the sort of easiest examples to play with. But all of the homework problems here are going to require you running the ratio test and then checking the endpoints. I'd like to look at one or two more examples, and then I want to kind of give you some concept stuff. So let's do one more like this. Let's find the IOC and ROC for the series f of x equals sigma n from 0 to infinity, -1 to the n over 2n factorial times x to the 2n. So the center here is again 0. Right, because x to the 2n is x minus 0 to the 2n. And the coefficients, the cn's here, are -1 to the n over 2n factorial, thereabouts. So we're going to run the ratio test. L is the limit as n goes to infinity, absolute value an plus 1 over an. Definitely not geometric because of this factorial shit going on down here. This is, I'll continue it down here, equal to the limit, n goes to infinity, absolute value of -1 to the n plus 1 over 2 parentheses n plus 1 close paren factorial times x to the 2 paren n plus 1. So there's an plus 1. And now we're going to multiply by the reciprocal of an, which is 2n factorial over -1 to the n x to the 2n. Like this. And just like in the previous example, I'm going to combine the pieces that kind of go well together. I've got an x to the, I can distribute this 2, that's 2n plus 2 over x to the 2n times -1 to the n plus 1 over -1 to the n times 2n factorial over 2n plus 2 factorial. Now again, here I distributed the 2 over the n plus 1 to get 2n plus 2. X to the 2n plus 2 over x to the 2n is x squared. I'll give each piece their own absolute value at this step also. -1 to the n plus 1 over -1 to the n is -1 to the 1, or just -1. 2n factorial over 2n plus 2 factorial is 2n times 2n minus 1 times 2n minus 2, all the way down to 3 times 2 times 1. That's 2n factorial. 2n plus 2 factorial is 2n plus 2 times 2n plus 1 times 2n times 2n minus 1 times 2n minus 2, all the way down to 3 times 2 times 1. And you see the cancellation here. So what we get for our ratio test limit here, the absolute value of -1 is 1. The absolute x squared can come out. So I get absolute x squared times limit n to infinity 1 over 2n plus 2 times 2n plus 1. And as n goes to infinity, 2n plus 2 and 2n plus 1 both go to infinity. So this is absolute x squared times 1 over infinity. That's 0. So here, L is the absolute value of x squared times 0, which is definitely always 0, which is definitely always less than 1, no matter what x is. So no matter what you take for x, the ratio test limit here, L, always comes out to 0. It's always less than 1. This tells us my series f of x equals sigma n from 0 to infinity -1 to the n over 2n factorial times x to the 2n converges absolutely for all real numbers x. The IOC, the interval of convergence, is -infinity to infinity. And the ROC, the radius of convergence, is plus infinity. So this is one of these interesting cases, right? If L comes out to the absolute value of x, or absolute value of x squared times some number, then you have to solve the inequality L is less than 1 in terms of the variable x. Here, L came out to 0. L is always 0 no matter what you plug in for x. And 0 is always less than 1. So no matter what you plug in for x, this series will always pass the ratio test. In other words, this series always converges. Doesn't matter what you plug in for x, this series always converges. Such a series, we say, has an infinite radius of convergence, and the interval of convergence is the set of all real numbers, interval -infinity to infinity. It's not terribly hard to do these calculations. Right? You just run it through the ratio test, and then you solve the inequality L is less than 1. And in the cases where you have a finite value there, you end up with a specific interval, then you have to test the endpoints. But it's all shit that you've done before. I think the real challenge in this section is to try and understand what a power series is and what it looks like or could even mean for a power series to converge to something. We're used to our series being series of numbers. You add up a bunch of numbers and you get another number. But here your series has some variables in it. So I want to take a second and just talk about the partial sums of a power series real quick. And I want to look at the one that we just played with. If I start writing out the terms of this series, when n is 0, I get 1 over 1 times x to the 0, that's 1. Then when n is 1, I get minus x squared over 2 factorial. When n is 2, I get plus x to the 4 over 4 factorial, and so on. Minus x to the 6 over 6 factorial, plus x to the 8 over 8 factorial, minus x to the 10 over 10 factorial, and it goes on. This is like a big long polynomial. So the partial sums of this power series really are polynomials. The 0th partial sum is 1. The first partial sum is, you could say, it's 1 minus x squared over 2 factorial. And then the next one is 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial. And then the next partial sum is 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial. I want to start graphing these polynomials for you in Desmos. After you have written down what I have here on the paper, you don't need to write anymore. Go ahead and get this written down. Make sure you're comfy seeing where these terms come from and why these are the partial sums. Once you get this written down, you can put down your pen, and we're going to move over to Desmos, and I just want you guys to look at some shit with me. All right, moving over now. Can't help it. Let's get rid of these. These are not the ones we're going to play with. Remember, I said our series is centered at 0. So we're paying attention to things kind of being built out from this point. My first partial sum, or the 0th partial sum, was just 1. And then the next partial sum was 1 minus x squared over 2 factorial. Then the next one was 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial. And then the next one was this plus x to the 6 over 6 factorial. And let's keep writing these in. The next one would have been, oh wait, sorry, they should be alternating sign, plus, minus. Minus. And then plus x to the 8 over 8 factorial. And then we'll do one more. Minus x to the 10 over 10 factorial. Okay. So follow with me here. And change this green to a red. Let's make it stand out a little better. Okie doke. So the red function here, this is cosine. if you start looking at the first few partial sums, what do you notice? The purple is doing a damn good job of sticking close to the red. And as I add more and more terms in this series, the purple is doing a better and better job of sticking close to the red, as long as you stay near the center. Right? And as I give more and more terms to this series, the purple is going to do a better and better job of sticking close to the red. Imagine that the red function was really hard to work with. Right? Cosine's not hard to work with, but imagine it was some other function that is really hard to, say, integrate. I don't know how to integrate the red function. I want to find the area under the red function now. Well, shit. Maybe I should try just finding the area under the purple function instead, because they are so friggin' close to each other. I can't even tell them apart. I think you would all agree that the area under the red function is about the same as the area under the purple function here. What's more, this purple function, although it might not be super nice, it's not hard to integrate because it's a polynomial. You just add 1 to each power of x and divide by that new power. It's not hard to differentiate. It's not hard to do anything calculus-wise to this purple function, although it might be hard to do stuff calculus-wise to the red function. Let me really mess with your head. Cos x over x. This is much harder to work with. But this isn't. Because you divide each one of these terms by x, you get something that's easy to work with. Red, very hard to work with. Purple, very easy to work with. And again, notice if I wanted the area under the red function, say from -4 to -2, I could just integrate the purple function instead. So this is the game. This is the game of the late part of chapter 11. I give you a red function. You try to find for me a purple function that is a power series that does a good job of approximating the red function. This is what it looks like to say a series converges to a function, right? To say that a power series converges is saying that the polynomials that are the partial sums of the power series are doing a good job getting close to the graph of the original function. I can show you one more of these before we go. I told you a long time ago that one of the series we played with was the series for e to the x. You'll notice the same sort of thing happening here. Oh. I start by looking at the red function and I pick a center. Here again, x equals 0. And then notice that this guy, he does a pretty good job of staying close to the red function as long as you stay really close to 0. But then this guy does an even better job. This guy does an even better job. This guy does a real friggin' good job. Look, everywhere between -1 and 1, I really can't even tell the purple apart from the red. And as you add more and more terms to the series, the purple and the red get closer together and they stay closer together longer. So this is what it looks like for a power series to converge. You have this sequence of polynomials that are getting closer and closer and closer to the graph of some function. Our goal is to figure out for exactly what values of x this sequence of polynomials will start gluing itself to this function. That's the interval of convergence. How are we doing for time here? Got just a few minutes left. So I'd like to show you maybe one more example since we do have time. I want to return to that geometric series example that we used at the very start. So our very first example, f of x was sigma n from 0 to infinity x to the n. This is definitely a geometric series. It's the series 1 plus x squared plus x cubed and so on. And it converges as long as the absolute value of x is less than 1. That is, -1 is less than x is less than 1. And in that case, the formula for the sum of a geometric series, remember, this is always the starting term over 1 minus the common ratio. Well, the starting term here is 1, and the common ratio is x. So this power series converges to this function.
Does that say converges as long as?
Yes. Yeah, it converges as long as. So this power series for x values between -1 and 1 converge to this function. In other words, the graph of this series has a graph, and the graph of this series is a part of the graph of 1 over 1 minus x. 1 over 1 minus x has a vertical asymptote at x equals 1. It's like this. If this is -1 and this is +1, then this is the graph of f of x. The full graph of 1 over 1 minus x looks like this. It goes on and on over here, and then it also has a piece down here. But the only part that is represented by the series is this black part, because that's the only stuff that's coming from the interval of convergence, -1 to 1. And I can demonstrate this too. We start looking at the terms of that series. Okay, here's 1 over 1 minus x, looking just as I drew it. So let's zoom in here and focus just on my interval of convergence, which is from -1 to 1. Let's change the color scheme to match the color scheme we were using before. Don't confuse ourselves any more than we have to. All right. Get rid of that. So see the red here? Let me turn this off. The red here looks like this. Here's my first partial sum, the next one, the next one, the next one, the next one, the next one. You see the purple kind of gluing itself to the red. It's stuck to the red right here. And then everywhere between -1 and +1, the purple is trying to glue itself to the red. I can give more and more terms. Here's going out to the 10th term. All right, and you see, he's trying a little bit harder to stick to that graph than he is. The later guy is doing a little bit better job approximating the red function. So as you let this series go all the way out and have infinitely many terms, it would actually be equal to the red function, but only on the domain -1 to 1. On that domain, the red and the purple are very, very close to each other. Like if I wanted to find the area under the red from 1 to, or from 0 to 1 or whatever, from 0 to 1/2, I could find the area under the purple instead. It would work great. You have to be careful about what happens at the endpoints here. This is why we need infinitely many terms. Finitely many terms, you can get into trouble. And that's why we have this full capital sigma notation, because we really do need a lot of terms to close up that gap at the end. There we go. So you're starting to see, right? The more terms I use, the tighter this gap gets. Here it wasn't very good. Back here it was quite poor. But if I use, like, instead of 8, 9, or 10 terms, I use like 16, 17, 18 terms, I'm able to close down this gap. And this function does a really good job of approximating this function, as long as you stay away from that problem point there at -1. Okay, so these are the kind of concepts, the basic ideas behind a power series. Power series are functions. The domain of those functions, the domain of the power series, is the interval of convergence. The way you find the interval of convergence usually is by applying the ratio test and then checking the endpoints. If you're extremely lucky, your series is a geometric series and you can skip using the ratio test and the endpoint stuff. Your homework for this week has you doing a bunch of just that, right? Like I give you a bunch of series that look like these and I ask you for the interval of convergence and the radius of convergence. It's not hard. There's a few questions like numbers 29 and 30, which will require you to think. These are not just straight calculation questions. You will have to put a little bit of thought in here. And I encourage you to think about the possible intervals of convergence. So you'll see these questions in the WebAssign homework. The other thing you will see in the WebAssign homework is a little bit of section 11.9. So representations of functions as power series. This is where you're going to be given the red function and try to come up with the purple function. At first, this is easy. At first, we just use this fact about geometric series and we make all sorts of cute little algebra tricks where we substitute things in. But it's going to get harder when we start talking about integrating and differentiating series. This week, I only gave you questions from the easy part of 11.9, and that's what we're going to talk about on Friday. And we're going to come back, we're going to talk about not how to find intervals of convergence, but how to use this sort of geometric series trick to get power series for some kind of basic functions like 1 over 1 plus x squared. Turns out that's not very hard to get. Or 1 over x plus 2, also not very hard to get. But then next week, we're going to start talking about integrating and differentiating power series. And then after that, we're going to start talking about Taylor's theorem. And then after that, we'll be done with power series. Hooray. But the integration and differentiation of power series is a little bit tricky. People tend to have a hard time with this. So you might want to read ahead just a little bit. Look at 1 or 2 of the examples here before class on Monday. But Friday's class won't be getting into any of this. It'll just be using geometric series and working more problems of the sort we saw today. And then Monday and Wednesday of next week, we'll be looking at integrating and differentiating power series and also Taylor's theorem. Taylor's theorem is kind of the culmination of all of this. It gives you a way of coming up with a power series for just about any function. As far as applications are concerned, Taylor series, most important single applied thing from like all of calculus. If you want to solve differential equations numerically, you want to figure out how water flows over, a boat, or how air flows over an airplane wing. It's all about these things, Taylor series. After we finish 11.10, you're done with series forever. You never have to touch series again, at least until you get about 2/3 of the way through differential equations. So you can take a big sigh of relaxation. And then we're going to start talking about some very different sort of application things. So that's where we are. That's the roadmap. Any questions for me before I let you guys go for the day?
No, sir. Thank you so much, Professor.
Yeah, of course. All right. If there's nothing else, I will see you guys later, either in office hours or at our next class on Friday. Take care.